Welcome to Aryabhat Center for Theoretical Physics. This is another video on the lecture series called Classical Field Theory. In the last lecture, I have derived what you call Lorentz transformation, and what Lorentz transformation does is to enable us to find from the coordinate of an event in one reference frame the coordinate of same event in another reference frame. So this Lorentz transformation basically connects one reference frame from the to the another reference frame. Now we can use this Lorentz transformation to relate the velocity of a material particle in one reference frame to the velocity of the same material particle viewed from the another reference frame. So how we what you call transform the velocity? Suppose there is a reference frame K which is at rest with we can say with Earth, reference system K at rest with respect to the Earth. Now there is another reference frame K dash which is moving with constant velocity v with respect to this reference frame K. Now we have to find the material particle which is moving with certain velocity, its component in this reference frame K dash. First of all, this whole movement is taking place in along the x-axis. So here is the Vx. Vx is the component of velocity in K system, dx by dt, and Vx dash dx dash by dt dash in the K dash system. We have to remember these two. Now we write this Lorentz transformation in differential form. So when we write the Lorentz transformation in differential form, it will become dx is equal to dx dash plus v dt dash divided by 1 minus v square by c square, dy dash dz is equal to dz dash, and dt is equal to dt dash plus v by c square dx dash divided by root 1 minus v square by c square. This is called differential form for the Lorentz transformation. Now what we do? We divide dx by dt. So when we divide dx by dt, it will simply become dx dash plus v dt dash divided by dt dash plus v by c square dx dash, because this common thing 1 minus v square by c square will cancel it out. So this is the form for dx by dt. Now what we do? We divide numerator and denominator both by dt dash. So when we divide numerator and denominator by dt dash, it will become dx dash by dt dash plus v divided by 1 plus v by c square dx dash dt dash. Remember we dividing this numerator by dt dash and this one by also dt dash. Now dx dash by dt dash is simply vx dash. So vx dash plus v 1 plus vx dash v by c square. This is the component of velocity of material particle in K reference system, is connecting the velocity of that same material particle in K dash system. Again Vy is equal to dy by dt, and it will simply become what you call Vy dash root 1 minus v square by v square c square plus 1 v by c square vx dash. This is for Vy, and for z component same thing, vz dash root 1 minus v by v square by c square 1 plus vx dash v by c square. This is the what you call velocity transformation. Now suppose that c velocity of light become infinite, or velocity v of this reference system become very low compared to the what you call velocity of light. It means v by c can be taken as almost 0. Then it will transform back to the transformation for the velocity in classical mechanics. So So Vy equal to Vy dash, Vz equal to Vz dash, and Vx equal to Vx dash plus V. So this is identical to the velocity transformation in classical mechanics. Now we have found the velocity transformation Vx, Vy and Vz. Suppose velocity of particle is parallel to the velocity of the system, then what will happen? Vy and Vz will become 0 and Vx, x component simply become V. And for the also for the what you call for the k dash system too, so it is V. So when we substitute this V in this one, it will become V equal to V dash plus V divided by 1 by V dash V by c square. Here V, this is big V, which is the velocity of the reference system. Now if velocity of the reference system is much less than velocity of light, then we can expand this one and this one and this one in the terms of V by c, and when we expand, it will simply become Vx is equal to Vx dash plus V 1 minus Vx square divided by c square, and Vy is equal to Vy dash minus Vy dash Vx dash V by c square, and this one Vz is equal to Vz dash 1 minus Vx dash Vz dash V by c square. This is the expansion of Vx, Vy, Vz in terms of V by c, and we can write these component form into single vector form. So V is equal to Vx plus Vy plus Vz, and finally it will become V is equal to V dash plus big V minus 1 by c square V dot V dash V dot V dash V dash. So this is general form for the velocity transformation when the what we call reference system k dash, velocity of the reference system k dash is much smaller than c. Now suppose in this there is another case where velocity of the particle is in the xy plane and it is moving, and its velocity is making theta with the what you call with the x-axis. Then we can write Vx is equal to V cos theta and Vy is equal to V sin theta for the k reference frame. Now when we are looking the particle velocity from the k dash reference frame, it will become Vx dash is equal to V dash cos theta dash, Vy dash is equal to V dash sin theta dash. Here sin theta dash is the angle in the k dash system, and from this, and when we substitute Vx and Vx dash, Vy and Vy dash in this, now we have derived the velocity of particle which lies in the xy plane and making angle theta from the x coordinate Vx, Vy and Vx dash Vy dash. Now we substitute this value in this velocity transformation law, and we will get what you call tan theta. Tan theta is equal to V dash root 1 minus V by V square by c square sin theta dash divided by V dash cos theta dash plus V. This is for when a particle velocity is making angle theta with the x-axis, or it is lie in the xy plane. Now suppose there is a known phenomena called aberration of light. In the aberration of light, we can substitute V and V dash equal to C, and when we substitute V and V dash equal to C, we will get tan theta is equal to 1 minus V square by c square sin theta dash divided by V by c plus cos theta dash. This is for the aberration of light, and from this we can find sin theta and cos theta. Now we have calculated what we call tan theta is equal to this much, and from this we can derive sin theta and cos theta value. Now this is for the case of aberration of light. Now suppose that V by C is much smaller than 1, then we can expand this one and we will get sin theta is equal to sin theta dash minus multiplied by 1 minus V by C cos theta dash, and sin theta minus sin theta dash is equal to minus V by C cos theta dash sin theta dash. Now we can calculate what we call angle of aberration. Angle of aberration delta theta is equal to theta dash minus theta. Now suppose this angle theta has changed from theta dash plus delta theta dash. This is the angle of aberration. Now you can substitute this one, theta is equal to theta dash plus delta theta dash, into what we call this one, and we will get sin theta plus delta theta dash minus sin theta dash is equal to minus V by C cos theta dash sin theta dash. Now we are taking the limit for delta theta dash goes down to 0, and we multiply this one by delta theta dash and delta theta dash. Numerator and denominator we have multiplied by delta theta dash, and we are taking delta theta dash goes down to 0. And when we take a limit, this whole term become cos theta dash delta theta dash equal to minus V by C cos theta dash sin theta dash, and cos theta dash cancel it out, we will get delta theta dash is equal to minus V by C sin theta dash, and we are taking delta theta is equal to minus delta theta dash, and we will get the angle of aberration angle delta theta is equal to V by C sin theta. This is called aberration of light, and this is angle of aberration of